Rightio, it is time for physics. Not just physics, but nuclear physics. Nuclear physics. Let's start with the easy stuff. Nuclear reactions. Nuclear reactions, they can be fission, they can be fusion, and they can be a few other things as well. So let's talk about fusion reactions. So, nuclear fusion. For example, where you get this guy, he's called deuterium. Dew meaning 2, mass number of 2 meaning he's got a proton and a neutron. This is the atomic number. 1 proton, this is the mass number, meaning 1 proton plus 1 neutron. Two nucleons, meaning deuterium. Plus, now he interacts with his cousin, tritium, three, mass number of 3, 1 proton, 2 neutrons, 3 nucleons all together. Anyway, the two of them together fuse. Now fusion means fusing together. If you put them together, you get a whole new element called helium. We know all about helium. Atomic number 2, hydrogen, helium, lithium, beryllium, etc. So 2 hydrogens together fuse to give you helium. But when you think about it, when you look at this, something's wrong. 1 plus 1 has to equal 2. Great, that happens, that's great. But 2 plus 3 does not equal 4. We actually have another product of this reaction, and it must be something with a mass number of 1 and an atomic number of 0. Something with 1 neutron and no protons. Now, what has 1 neutron and no protons? Tricky. Oh, I know. A neutron. So, neutron, 1, 0. See, there's an example of fusion. Now, what we've just seen is that in these nuclear reactions, atomic number is conserved. We've also seen that mass number is conserved. 2 plus 3 equals 4 plus 1. What is not conserved is total mass. Mass number, yes. Total mass, no. We'll get to that in a minute. The other thing that's not conserved is the amount of nuclear energy in each nucleus. That changes. And those two things are connected. The mass and the energy are connected. Anyway, that's one example. A second example could be an alpha particle bombarding nitrogen. So let's have, now this is an example of, now we'll get to fission in a minute. This is just another nuclear, well no, this is, yeah, okay, so helium 4, 2, that's an alpha particle. It bombards nitrogen 14, 7. Now, this happens to produce two new products. So we've got helium plus nitrogen. It gives us oxygen, which is 17, 8, plus what? If you know there's only one other product, what's it going to be? Well, 2 plus 7 gives us 9. This is 8, so it's got to be a 1. 4 plus 14 gives us 18. This is 17, so it's got to be a 1. The only thing that's got 1 proton and no neutrons is hydrogen. Normal, standard, Joe average, lunchbox hydrogen. Not one of these fancy, elaborate things here. This is hydrogen with a neutron. This is hydrogen with 2 neutrons. This is just standard Joe lunchbox hydrogen with 1 proton and no neutrons. Now let's look at an example of nuclear fission. Nuclear fission. Fusion and fission. By the way, do you know when nuclear physicists go to a takeaway shop, what they order? Fission chips. Sorry, that was awful. Okay, so fission is when you fire a neutron, 1, 0, at something big like uranium, 2, 3, 5, 92, and what it does is it splits this big nucleus up into 2 daughter nuclei, or 2 separate nuclei. So They could be, in this case, barium, which is 14156, plus krypton, 9236. Now, if you look at this, 235 plus 1 gives you 236. 141 and 92 does not give you 236, it gives you 233. So there's a slight problem. 92 is the same as 56 plus 36, that adds up. So what are we ending up with? We cannot have an unbalanced nuclear equation, that does not work. So you need another product. Now what has a mass number of 3 and an atomic number of 0? The answer? 3 neutrons. 3 times neutron. Now, what you've just seen is the makings of a nuclear chain reaction, which is what they use to make nuclear power stations and bombs. Because if you can get enough neutrons produced here, it will accelerate this process that you started here. You fire 1 neutron at uranium, but you end up with 3 neutrons. If that can all go into more uranium, that'll fire off 9 neutrons and then 27 neutrons, and you have a chain reaction and you have an uncontrolled nuclear explosion. And that's the basis of a nuclear bomb. Anyway, enough on that. Fission and fusion and how to balance reactions. Now we take a duster or a pair of socks. We rub this clean. And let's go back to the beginning. Let's talk about mass energy. I said that in nuclear reactions, mass number and atomic number are conserved, but actual mass is not conserved and energy is not conserved either. Why is this? How can this be? Well, the answer is because of Albert Einstein. He came up with an equation, E equals mc squared. Not super useful in that form. Much more useful if we put a little triangle here and a little triangle here. Now, think of it this way. If you get some protons and neutrons and you split them apart so they're a long way apart, and you find the mass of those individual nucleons, it'll give you a value m. You weigh each of them somehow, it gives you a mass m. Then you whack them all together, 1, 2, 3, 4, 5, however many there are, 5, and you find the mass is now reduced, it's less. M minus delta M. Delta M is what we call a mass defect. Now what happens is this mass is lost because there is a loss of energy by these guys as they are held together. We call it binding energy. They are held together with this nuclear glue and they've actually lost energy in the process. It's like they've fallen into a potential well and it's very hard to pull them apart. So because of that, this equation here helps us explain what's going on. The loss of mass is equivalent to energy that's released, and that's the energy in a nuclear bomb or a nuclear power station or in the centre of the sun. It's the energy that drives life, that keeps the universe going. Actually, it's God that keeps the universe going, but God created the energy that's released in nuclear reactions to allow that to happen. Now, let's have a look. You can draw a graph of binding energy per nucleon, and along here we can have mass number. So what we have is we have very small nuclei through to very large nuclei. So on the small end, if you look at where hydrogen is, it's down like this. Hydrogen, it's got a very low binding energy per nucleon, meaning the nucleus is not held together very tightly. Helium is up here. Then if you keep going, the most stable nucleus is iron. So we have this sort of rough kind of curved thing like this. And then what happens is it sort of goes down a bit like that. And right out this end we have uranium. Now what this means is there's kind of a watershed here. If you get two nuclei here and you fuse them together, fusion will release nuclear energy, because the product that you form will have more binding energy, which means binding energy is a negative energy, meaning energy is actually released in the form of heat and light. Okay, so fusion to create a bigger nucleus will release energy. Now on the other side here, fusion won't achieve you anything except to take energy. What you do is you split a large nucleus up. Over here we have fission. You split uranium into two daughter nuclei, and they will each have more binding energy per nucleon, meaning they've lost actual energy, because binding energy is negative. They've actually lost energy, and that energy has gone out in the form of heat or light in some way. So that's what happens when you fuse large nuclei, and this is what, when you split large nuclei, and this is what happens when you fuse smaller nuclei. Okay, third point. What actually holds a nucleus together? Now there's fancy elaborate diagrams, but just at a basic level, if you look at it, there are two forces acting on the nuclei, acting on subatomic particles in a nucleus. Now think about the fact that you have a whole lot of protons that you're packing together in a small space. Protons repel each other because of the electrostatic force, or the Coulomb force they call it. So if you think about, this is distance. Now these units are going to be very small, like femtometers, 10 to the minus 15 meters, but you're talking very small distances. Electrostatic force